looking at these, and we'll start off with number 1. This is all from momentum, of course. So the big idea with number 1 here is that when things collide, momentum is always conserved. But kinetic energy sometimes is and sometimes isn't the same before and after. And that's all that being conserved means. It means that the momentum initially has to equal the momentum final. And that would be true in any collision. Whether the collision is elastic, where things bounce off of each other, or like this one, inelastic, where they stick to each other in some way. So, let's look at the initial and final momentum and figure some stuff out, and then we'll look at the initial and final kinetic energy. But we know these two have to be the same. So you have a 1 kilogram lump of clay sliding to the right, frictionless surface with this speed. And the metal sphere is sliding to the left. So, we have the clay, and it's moving, and it's got a mass of 1 kilogram, and it's going to say moving to the right at 2 meters per second. Now, direction makes a big difference here. Let's assume that right is positive. That means the steel, which is moving to the left at 4 meters per second, we're going to call that 4 negative. And it's got a mass of 0.5 kilograms. So this is all right here, the initial momentum. So we have to combine the two. Well, we have a positive 2, m times v is positive 2, and here we have negative 4 times that. This will be a negative 2, isn't it? Make sure I get that right. Half of 4 is 2. So I have a positive 2 and a negative 2, so my initial momentum is actually 0. So when they collide and stick together, their momentum afterwards has to be 0. But if they're one object, then to have a momentum of 0, to have your final momentum be 0, there's only one way to do that if you're a single object, and that's your velocity has to be 0. Well, wait a second, if your velocity is 0, then what's the kinetic energy of the combined objects? Well, it also has to be 0, because there's no velocity. There was kinetic energy here, because remember, direction doesn't matter, but after the collision, there will be no kinetic energy. It was all absorbed in the friction in the collision. So I would go with D. That would be correct. All right. 2 kilogram object traveling 5 meters per second. Frictionless horizontal surface collides head-on with and sticks to, so that's an inelastic collision. A 3 kilogram object initially at rest. Okay, so let's do the momentum first, because we know that's conserved. So the momentum initially, before they collide, has to equal the momentum final. And initially, you just have a single object that's moving, the other one's at rest. So all the momentum is with that first object. And it is a 2 kilogram object moving at 5 meters per second. So the first object there has 10 kilogram meters per second worth of momentum. The 3 kilogram object doesn't have any, so there's your initial. That has to equal your final. But now, they collide and stick together. So your final momentum, though, while it has to be this, is now got a mass of 5 kilograms because they stick together. And so I have to find the new velocity that will give me the same momentum that I had before. And so that's quick division should get me that the final velocity is 2 meters per second. So the two of them combined is only moving at 2 meters per second. Yet they still have the same momentum because there's more stuff. Now, what's the correctly identified change in kinetic energy? So let's go back to the beginning. The kinetic energy initial would have been 1/2 the mass of this object, the only one that was moving, 2 kilograms, times its velocity squared, which would be 25. So its kinetic energy would have been half of 2, which is 1, so it would have been 25 joules. That would be the initial kinetic energy. What about the final kinetic energy? Well, now, in the final situation, we have a 5 kilogram object, so that's 1/2 times 5, moving at 2 meters per second, so that's 2 squared, that's going to be 4. And so I end up with 10 joules? Yeah. So my kinetic energy dropped. In the process of sticking together, there was energy lost to friction. So inelastic collisions, kinetic energy is not conserved. It's only in purely elastic collisions. So I would say the kinetic energy decreases, and the final speed afterwards is 2 meters per second. So I would go with C. All right, number 4. A dog of mass 10 kilograms sits in a skateboard of mass 2 kilograms that is initially traveling south at 2 meters per second. The dog jumps off with a velocity of 1 meter per second north relative to the ground. Which of the following is the best estimate of the velocity of the skateboard? Okay. So initially, I'm just going to say south is this way, and we'll call that positive, and north is this way, and we'll call it negative. So initially, you have the skateboard, and you have the dog. There's your dog. Looks like a platypus, but it works. It doesn't even have legs. Give it a tail. Alright, like a dodo bird. But anyway, all we care about is that the initial momentum here is 12 kilograms moving at 2 meters per second. So total of 12 kilograms between the dog and the sled or the skateboard, and it's moving 2 meters per second to the right. We'll call that positive. So the initial momentum is 24 kilogram meters per second. Now when the dog jumps off, here's what we have to keep in mind. All the forces are internal to the board and the dog. So if we consider the system to be the board and the dog, when they're done, the momentum still needs to be 24 kilogram meters per second. But here's what's interesting. When the dog jumps off, he's going to be going the other way at 1 meter per second. He's got 10 kilograms. So the after situation is the dog, this is just now the dog, moving at -1 meter per second, and he has a mass of 10 kilograms. So his momentum is -10. What is the momentum of the skateboard got to be? Well, see, in order to jump backwards, the dog has to push on the skateboard that way. So the skateboard is going to speed up. How much? Well, here's what I need. Because the forces are internal, I need this final momentum to equal the initial. So the final momentum is the momentum of the dog, final, plus the momentum of the skateboard, final. And I know it's got to equal what everything had at the beginning, 24 kilogram meters per second. But I've already got this nailed down for the dog. It's -10. So I need this. So if I add 10 to both sides, the momentum of the skateboard afterwards is going to be 34 kilogram meters per second. Now, that's the momentum of the skateboard after the dog pushes off. But you'll notice that's not one of your answers. They want the speed of the skateboard. We're almost there. The momentum of the skateboard at that point is going to be the mass, which is 2 kilograms, times that speed they're looking for, is going to equal 34. So I divide that, the final speed of the skateboard should be 17 meters per second. And it should be continuing to go south, because the dog pushed this way, so it's going to push the skateboard. So I would go with E. And that is correct. A kitten sits in a lightweight basket near the edge of a table. A person accidentally knocks the basket off the table. Careless. As the kitten and the basket fall, the kitten rolls, turns, kicks, and catches the side of the basket in its claws. The basket lands on the floor with the kitten safely inside. Okay, great, thanks. If air resistance is negligible, what is the acceleration of the kitten-basket system while the kitten and the basket are in midair? Well, they're both in free fall. So it's just, they said air resistance is negligible, so don't give me this basket is light bit. Yeah, I would just go with B. It's a projectile. It's an awful lot of words just to say what happens when something falls. It's number 6. Yeah, it's B. No. The center. See, that doesn't affect the center of mass. Everything the kitten does is internal to the system, so the center of mass for the system stays. And how hard it was knocked off, it could be thrown down. The acceleration would still be 9.8. And the only reason the basket being light would be an issue is if there's air resistance, but there's not. So, yeah. Person of mass 60 kilograms sliding along level ice at a speed of 3 meters per second collides with a second person who is initially at rest. Assume that friction is negligible. If the two people hold on to each other, and their common final speed after is 2 meters per second. Okay, now what's the mass of the second person? So, classic momentum initial has to equal the momentum final. I kind of like setting them apart like this. Now, initially, I have one object that's moving, the other person is at rest. So I have a 60 kilogram person moving, we'll say to the right, positive, at 3 meters per second. Afterwards, I have a single object whose mass is 60 plus the mass of the second person. I don't know what that is. But I do know that their speed afterwards is 2 meters per second. So these two have to be equal, momentum before, momentum after. So this is 180 kilogram meters per second equals, I'll do it this way, equals 120 plus 2m2. So I'm going to subtract 120 from both sides and get 60 equals 2m2. And that means I would get the mass of the other person as being 30 kilograms. That's answer B. I'll check my answers, and that is correct. So just classic setup, before and after. Who has the momentum? Might be more than one thing, but in this case, just one thing had the momentum. What's the momentum look like afterwards? In this case, it's a combined object, inelastic collision. All right. Railroad car, mass m, moving with a speed v, I assume it's v, when it collides and connects to a second railroad car of mass 3m, initially at rest. Alright, so what's the speed and the kinetic energy? Well, we'll start with the initial momentum was all in this car, so it's just mv. And that has to equal the final momentum, which is going to be, well, the final momentum is going to be the total mass, 4m, times this new velocity called v final. So the speed, you look at it like this. I got mv has to equal 4m v final. The m's are going to go away, so I could do it this way. The m's divide out. I'll divide by 4. That would tell me that the final velocity is equal to a fourth of the original. I think I like that. It's less. This would make sense. It would hit, and they would have more mass, so the velocity would have to go down. Fair enough. Now the kinetic energy. Well, let's see. Initially, I would have 1/2 mv squared. That'd be the kinetic energy initially. What about afterwards? Kinetic energy final would be 1/2 4m v over 4 squared. So these 4's are not going to cancel necessarily. This one's going to go away, but this is going to be a 16 in the bottom. So it's still going to be a 4 in the bottom. So this is going to be 1/2 mv squared all over 4, we'll say. That's one way to look at it. So it's going to be a fourth. It's going to be less kinetic energy. You're going to generally lose kinetic energy in an inelastic collision. So the speed is less, and the kinetic energy is less. So that gives me an answer of A. But the momentum before and after is still the same. Toy cannon is initially at rest on a horizontal surface when it launches a 0.05 kilogram projectile with a velocity of 10 meters per second at an angle of 60 above the horizontal. Alright, this is actually an interesting question. So, by launching it at a 60-degree angle, there is that 10 meters per second, I'm just going to call that 10 meters per second. The vertical part of it is going to make a difference because the table is going to exert a normal force, which is an external force. And so really the only part that's going to move the cannon is the horizontal component of this. So we need to figure that out. If this is 60 degrees, I want the original velocity's x component. I want 10 meters per second times the cosine of 60. And I believe the cosine of 60 is a half. Let me double check. Yeah. So that means all that really matters is the x component here is 5 meters per second. So, horizontally speaking, the initial momentum, by the way, of the whole system is 0. Because the cannon is at rest with the bullet or whatever, the toy projectile inside of it. The final has to also equal 0, but the final is now consisting of 2 parts. It has the momentum of the cannon plus the momentum of the projectile. And we are only worrying about the horizontal parts here because the normal force is going to act as an unbalanced or external force. So really what we come down to is the 2 momentums are the same except opposite. One's going to be positive, one's going to be negative. In fact, we'll see the cannon's negative. So I have the momentum of the projectile. I think I can get that I'm going to bring this over here. So I got 0.05 times what I believe is 5 meters per second equals the cannon, whose mass is 1 kilogram, whose velocity I don't know. And it's going to be the opposite sign. So if I do these two times each other, that's going to be 0.05 times 5, 0.25 divided by 1. So it's just V final for the cannon should be, V cannon final should be negative 0.25 meters per second. Recoil backwards. They just want the magnitude, I guess, or speed. Say speed, so that doesn't matter. So I would say A. Let me just double check the answer, and I'll be right. All right. So the initial momentum before the cannon's fired is 0. Afterwards, you can't use all 10 meters per second because the vertical component of that is going to get canceled out. So the cannon's going to push down on the normal on the table, but the table's going to push back up on it. Whereas the cannon's going to push the ball horizontally, and nothing's going to be there to push back, so the cannon's going to recoil. So it's only the horizontal component that matters. An empty sled of mass m moves without friction across a frozen pond at a speed VO. Two objects are dropped vertically into the sled at one at a time. First an object of mass m, and then an object of 2m. Afterwards, the sled moves with a speed of v final. The order would not make a difference. Really, you could look at them, they could be dropped in at the same time. It doesn't matter. The two momentum, since the masses aren't thrown in sideways, there's no momentum added in or anything, so it's got to keep the same momentum if things are dropped in vertically, if something's moving horizontally. So the initial momentum is mvo. That has got to equal, well, basically, it would be the same v final. The order should not make a difference. So really, we don't have to do any calculations. If all they're saying is if they're dropped in different order, doesn't make it. It's the same. So whatever your v final would be. So like you would add in m plus 3m's, the two of them. It doesn't matter the order they're dropped in. And then this would be your v final. And it wouldn't matter, the order. So yeah, it's just that. 12. Sorry about the copy on this one. It's a little messy. An ice skater is moving at a constant velocity across an icy pond. Skater throws a snowball directly ahead. Which of the following correctly describes the velocity of the center of mass of the skater's snowball system? Careful. Not the velocity of the skater or the snowball, but their center of mass immediately after the snowball is thrown. And they're saying no external forces. So all the forces are are internal. So between the snowball and the skater, so the velocity of the center of mass will not change. It is equal to the original velocity. The original velocity of the skater is what the holding the snowball. I believe it should be that still. The skater might slow down a little bit, and the ball will go forward and speed up forward, obviously, but it'll still maintain that same velocity. So this is 12. Let's just make sure. Yep, D is correct. So what you want to look for is if the forces are internal, the velocity of the center mass will remain unchanged. 15. A ball of mass m and speed v collides head-on with a ball of mass 2m and speed v/2 as shown. if the two balls stick together, their speed after the collision is pretty much a straight momentum initial equals momentum final. I like to spread them out like this. Here we have both of them are moving initially. So if we call this way positive, sorry, you can see that on there. If I call to the right positive, that means I have a positive mv and a negative, let's see, well the 2's are going to cancel, so I have a negative mv, because when I multiply v over 2 times 2m, the 2's are going to cancel, I'm still going to have mv. So my initial momentum is 0. They stick together. That means that their new mass is 3m. But I don't really care, because their new velocity has to be 0. Because if they're one object and they have no momentum, if you're two objects, you can have 0 momentum and both of you can be moving, like here. But if you're one object and you have 0 momentum, the only way to do that is not be moving. So I would go with A. Alright, and I think we're on the last one. I think 17, 18, and 19 all deal with the same graph. This ought to be interesting. So, a block 1, represented here, mass 1, and block 2 of mass 2, are sliding along the same line on a horizontal frictionless surface when they collide at time t0. The graph shows the velocities of the blocks as a function of time. Alright. So, I have, just real quickly, an initial momentum of 4m1 plus negative m2, because this one was moving at -1, this is moving at 4. They don't say that the masses are the same, so I can't necessarily combine those, but I would say that's your initial momentum. They combine afterwards, and they have a momentum, a final momentum of, and this would be m1 plus m2, and now they're moving at 1 meter per second. So this and this are equal to each other. Well, if we want to find the kinetic energy, if they collide and stick together, I can almost tell you it's got to be less. I'm kind of liking the internal energy, or the heat thing here, because it's got to be less. Direction doesn't matter for kinetic energy, so I would rule out this. I would go with this. It's got to be less, and it's because it's transformed into heat. Just let me double check. Yes, I would be correct in that one. But it's got to be less. You always lose in an inelastic collision. You lose kinetic energy. Let's keep this stuff in mind, by the way, because I think it's going to come up. So 18. It says, which block has a greater mass, and what information indicates this? Well, let's see. The 2 hit. I have 4m1 minus an m2 comes out to be m1 plus m2, because you figure that 1, like we have, they end up with a velocity of 1. So I could do this. I could do add m2 to both sides, so I could end up with 3 m1s by subtracting m1 from both sides, and then adding it equals 2 m2s So then it's always tricky to interpret this. That means M2 has the bigger mass, because 2 of them equals 3 of these, so this must have the bigger mass. Now, I just did it algebraically. Let's see. I would say block 2. Block 2 because it has a smaller speed before the collision. Not sure. Block 2 because the final velocity is closer to the initial velocity of block 2. So this one's velocity dropped drastically. So that's not a bad way of looking at it. The smaller object is going to have the larger change of velocity in a collision like that. Think of a bug flying into your windshield, right? The bug experiences the much larger change in velocity, even though the impulse for you is the same. This one only experiences a change in 2, so yeah, okay, I would go with block 2 because the final velocity is closer to that. I would go with D on that one. 18, D. All right, so far so good. Third part of this thing. Which of the following is true of the motion of the center of mass of the 2-block system during the time shown? Oh, come on now. You know this. You know this. If all the forces are internal, if the 2 blocks are just hitting each other, nothing else external is acting, then the center of mass, then the motion of the center of mass will remain unchanged. Now, the motion before, if they want to know, center of mass velocity does not increase. The center of mass velocity starts out greater than 1, but no. It's going to move at a constant velocity. Center of mass does not move. Okay, well, let's see. Initially, I have block 1 moving at 4, and it has a mass of 1. And block 2 has a mass of 2, is moving at -1. The center of mass of that system. Later, we did find out that if we wanted to, we could describe, say, block M1 is 2/3 of M2, so I could say this is 2/3 of M2 minus M2. That give me 8/3 M2s minus an M2. So that'd be 3/3. That'd be 5/3. So it would be positive. The center of mass would have a positive velocity. Okay, but the center of mass, was it moving before? Center of mass does not move because the blocks are moving in opposite directions before the collision. I don't buy that necessarily. The center of mass moves at a constant velocity of 1 meter per second because there's no friction acting. So, am I missing something with my analysis over here? Because they say the velocity would be 1 meter per second. So I must be missing something. Let's just make sure. I got 4m1 minus 1m2. This is the momentum before. What would the velocity of their center of mass be? Well, their center of mass would be a spot between them. Do they say how far away? This is their velocity. And they collide. I'd be hard-pressed to come up with why it's 1, but I wouldn't say that it's not moving. And it's not going to change. Neither of these work because all the forces are internal, so there's not going to be a change. So I can get it down to A and B. I'm a little hard-pressed right now to figure out why it's 1, but of the choice, I do like B better. And that is the 19. So you got it down to A and B and you make a guess. That's fine. B is the right answer. I'll look at it some more and see if I can figure out why the center mass is moving at 1. All right. Then we'll do the rest of it later on.